Today we're backing up to section 5.1. We have talked about local minimums and local maximums. And we've talked a little bit about absolute maximums and absolute minimums, but today we're going to really focus on those. Okay? So absolute extreme values. So let f be a function with domain D. The domain may be all real numbers, but it could be that we have a domain that is a subset of all the real numbers. So f of c is an absolute maximum value of f on D if and only if f of c is greater than or equal to f of x for all x in D. Notice that you can have more than one place where you have your absolute maximum. Likewise, f of c is the absolute minimum value of f on D if and only if f of c is less than or equal to f of x for all x in D. So think about it this way. So let's say that you love track and field. And you are watching a competition where they're running multiple heats of the 100-meter dash, right? Is it possible that more than one person has the fastest time? Yeah, they could have exactly, do they go to the hundreds of seconds? I think. It could be even to the nearest hundredth of seconds. There are two people that have exactly the same time. That's okay. It's still the fastest time. It is the minimum time. Okay, so a minimum can occur at more than one point. Notice also that the minimum is the time, not the number of the person who ran it. That just identifies who. Okay? So, absolute or global maximum or minimum values of a function are also called absolute extrema. A lot of times they just skip the word absolute and or global and just say maximum or minimum. The maximum, the minimum, as opposed to a local maximum or a local minimum. So the extreme value theorem, this came up on a homework problem the other day, and I said, we're going to talk about this later if I remember correctly. The extreme value theorem says that if f is continuous, doesn't have to be differentiable, just continuous, on a closed interval from a to b, then f has both a minimum and a maximum value on the closed interval from a to b. So just as an example, if our function is y equals sine of x, what's the maximum value of the function? 1. What's the minimum value? -1. Does it matter that it happens at lots of different places? No, that's still the maximum and still the minimum. Occasionally a student will, in thinking about this, and it's not a bad thought, they're like, wait a minute, what if it's a constant function? Like y equals 7. Well, what's the maximum value? 7. What's the minimum value? Also 7. Okay, it has a maximum and it has a minimum. If you have a continuous function on any kind of an interval, on any kind of a closed interval, you will have a minimum and you will have a maximum. Now, it has to be a closed interval. The reason it has to be closed is because, well, what if you had something like that, where what should be at the end of this segment on both ends doesn't exist? Well, you don't have a maximum or a minimum then. You have almost this. All right. Extreme values of a function occur only at either critical points or endpoints of the function's domain, although not every critical point or endpoint signals the presence of an extreme value. You're like, okay. So if you have something, you don't need to draw this, that looks like this. This is the location of the absolute minimum. This is the location of the absolute maximum. Here we have, what are we going to have at these points? Local mins and local maxes. And at this end point, depends on which textbook you use as to whether they call that a local minimum or not. Some books say yes, some books say no. College Board avoids it by always making these, intervals the right kind of intervals. Okay, turn it over to the next page, the candidates test. Your book doesn't call this the candidates test. I've never heard it called anything else by anybody associated with the College Board. They all call it the candidates test. I don't know if it's called the candidates test in other calculus textbooks. I just haven't looked at enough of them. But it's a pretty easy idea. And it says this, but an important idea. If f is continuous on the closed interval from a to b and has critical points between a and b, say x equals c sub 1, x equals c sub 2, etc., then the maximum and the minimum values of f on the closed interval from a to b may be selected from f of a, f of b, f of c sub 1, f of c sub 2, etc., etc., etc. So the reason it's called the candidates test is your candidates for where the maximum or the minimum are going to occur are either endpoints or critical points of the original function. Then you test them to see, well, which one is bigger and which one is smaller. This is very different than what we've been doing. We've been making local arguments. If the derivative changes from positive to negative at a point, the function changed from increasing to decreasing, and we have a local maximum. Here, we don't have to do that. What we're going to do is going to find all the candidates, and then we're going to test the candidates, and then we're going to see who wins. Okay? This is more like, you identify who's running, and you can find out at the end who was fastest and who was slowest, and what the fastest time was and what the slowest time was. So, let's take a look. Find the maximum and minimum values of x to the 2/3 on the interval from -8 to 1. Okay, so first we need to identify our candidates. We already know two of them. Two possible places where we could have a maximum or a minimum are at x is -8 and x is 1. But we also need to find, are there any critical points? So f prime of x is 2/3 x to the -1/3. Is there any place where this doesn't exist? Always look for doesn't exist first. At x is 0. Because remember, the negative exponent means that x is on bottom. So this has a critical point at x equals 0. So now we've identified the three candidates. All I have to do now is make myself a handy-dandy T-chart and test each of the candidates. In the original function. So, -8 to the 2/3 power. What is that? Yep, it's 4. -8 to the 1/3 is -2, and -2 squared is 4. 1 to the 2/3 power is 1, and 0 to the 2/3 power is 0. Pardon?
If you went a negative number then a positive number then 0.
Yeah, it is a little different. So, what is the maximum? The maximum is 4. -8 is where the maximum occurred. Right? Y'all understand the difference between the two? And the minimum is what? Is 0. And that's it. Okay, now, I know some students who will do this, and it's not a bad idea. They'll write the maximum is equal to f of -8, which is 4. The nice thing about that is that tells you not only what is the maximum, but it also tells you where it occurs. Is it necessary? Absolutely not. Okay, because all it asks is what is the maximum and what is the minimum. By the way, if you're curious, what does this graph look like? It looks like a kindergartner's seagull. And you can see that this is going up. So over here at -8, that's going to be the highest point. Whereas over here at 1, that's going to be less. And at 0, that's going to be your lowest point. All right, let's try one where I have no idea what this graph looks like. Find the minimum, maximum, and minimum values of f of x is 3x over 1 plus x squared on the closed interval from -4 to 2. Again, the extreme value theorem guarantees me I will have a maximum and I will have a minimum if I have a continuous function on a closed interval. Well, I certainly have a closed interval. Is this function continuous? Is there any place where this function does not exist? No, because the denominator is never negative, the denominator is never 0. So I'll look for critical points. Can I simplify this at all before I start looking for those? No. I don't have any choice but to use the quotient rule. So that'll be 1 plus x squared times 3 minus 3x times 2x all over 1 plus x squared quantity squared. Are there any places where the derivative doesn't exist? No. The denominator is never 0, so that's fine. And if I want this to be equal to 0, if I want a fraction to be equal to 0, what part of the fraction do I need to look at? Yeah, the numerator. So this will be 3 plus 3x squared minus 6x squared is equal to 0. So that's 3 minus 3x squared is equal to 0. I'm going to factor out a -3 so that I get x squared minus 1. So that's going to be x is equal to plus or minus 1. This time I have 4 candidates. You never know how many candidates you have until you find the critical points. So -4 and 2 are 2 of my critical points, 2 of my candidates, and -1 and 1 are also candidates. Let's see who wins. So we substitute in -4, that's -12 over 17. Ugh. See, that's going to be 6 over 5. This will be negative 3 over 2. And this will be 3 over 2. So let's look at the two negative ones. Which one is further to the left? Negative 12/17 or negative 3/2? Yeah, negative 3/2. So the minimum is negative 3/2. Then which one is further to the right on a number line? 6/5 or 3/2? 3/2. The maximum is 3/2. And now I'm super curious as to what the heck this looks like. So clear that. Clear this thing out. Do my horizontal fraction bar. And I only want this from negative 4 to 2. And it never went particularly high or particularly low. So I'm going to say, go from negative 2 to 2. And it should all be in there. Oh, okay. That confirms what we found. If I trace this to negative 1, we do get the lowest point in that window. And if I trace it to positive 1, I get the highest point in that window. Pardon? And you said you like how that math works out? Yeah. That's one of the things that is appealing, I think, about some of math, at least, is that you feel that it's more definite than other things. All right.